One more example of exponential decay has to do with what's called Newton's law of cooling. So Newton's law of cooling has to do with describing the temperature of some object that you bring into a room which has an ambient, a steady ambient temperature. So this is things like you put a steak in a 400-degree oven, or you put something in a 35, 37-degree refrigerator, whatever. So the idea is that you have some sort of like ambient space, like an oven or even a room with a temperature of 72 degrees or whatever, or a fridge, whatever. You have some state that has an ambient temperature, and then you're going to introduce some object into that ambient space and figure out how does that object change its temperature. And the rate at which it does is what's called Newton's law of cooling. Newton's law of cooling basically just says temperature changes exponentially. And so if the temperature of the object is capital T, and let's say that this is the capital T is the temperature at time T, where T, let's just for sake of argument say T is in minutes. It can be in whatever unit you want it to be. Then the rate of change of the temperature is going to be proportional to the temperature minus the ambient temperature. Okay, so this is the ambient temperature of, so this is the ambient temperature of whatever space you're introducing this object to. So the oven, the room, the refrigerator, whatever. Okay, and so if we solve our differential equation here, and I'll let you work out the details. I really want you to try out the details here. It turns out that we're going to end up with the temperature being the ambient temperature plus the initial minus the ambient temperature, e to the minus kt. So it's a separable differential equation. This T sub a, by the way, is a constant. So you can just divide both sides by this quantity. You have to take natural logs, solve for it. Again, you should definitely do this. So pause the video, try and come up with this formula, and then T naught is the temperature of the object at time t equals 0. Okay, so that's what Newton's law of cooling says about the temperature. And notice, by the way, that the formula is really simple, but the differential equation is even simpler. So this is one thing that's nice about differential equations, is that you can describe the same system in a much simpler way using differential equations. Okay, and so that's clearly preferable. So what I want to do is let's do an example. With this. So let's say that a steak needs to be cooked to an internal temperature of 140 degrees in order to be safe. And then after that, we want to chill. So we want to chill the steak to 42 degrees. So we place it in the refrigerator. So we place it in the refrigerator, which is set to 37 degrees. Okay, and so the question is, how long do we need to keep the steak in there? And we need one more data point. We check the temperature after 2 minutes. And after 2 minutes, the steak is cooled. After 2 minutes, the steak is cooled to 124 degrees. Okay, and so how much longer? Let me actually word this just slightly differently. How long do we need to cool it? How long? How long does the steak need to stay in the refrigerator in order to cool it down to what we want, 42 degrees? Okay, so we start with a cooked steak at 140 degrees, pop it right in the oven. against all cooking advice. And I'm sorry, we pop it right in the refrigerator. The refrigerator set to 37. We want it to cool to 42. And then we have this one other data point that after 2 minutes, the temperature is 124. So what we're going to do is we're going to take our temperature, our equation for the temperature, and we know that that's going to be the ambient plus the initial minus the ambient e to the minus kt. And the first thing that we're going to notice is that, of course, we can fill out the ambient temperature and the initial temperature right away, but we're going to have to figure out what K is. And that's what our initial data point is going to help us with. So let's do this. So we're going to have, I might as well just do this in 2 steps here. Our ambient temperature is 37. Our initial temperature is 140. And we have to find K. We know that T of 2 on the one hand is going to be 124, and on the other hand is going to be 37 plus 103 e to the minus 2k. And then we can solve this equation for k, and what we would get would be, let's see, we would have the natural log of 124 minus 37 over 103. That's all divided by -2, and that'll be our k. Okay, and when we do that, what we're going to get for k is we're going to get k is 0.08441. So this tells us that the equation that we need to work with is 37 plus 103 e to the minus 0.08441 t. And then finally, we have to solve capital T of capital T equals 42 for little t. Okay, so we have to solve capital T equals 42 for little t. And when we do that, we're going to end up with 42 is 37 plus 103 e to the minus 0.08441 t. And from here, we can simplify, take logs, and t is going to end up being the natural log of 42 minus 37 over 103 divided by our negative k, 0.08441. And this is going to lead us to be 33.84 more minutes. Okay, 33.84 minutes, I should say. Okay, and so that gives us an idea of how long we need to keep the steak in the fridge. So 33.84 minutes total. That means 31.84 minutes after we checked. Okay, so however you want to interpret that.